Our next talk is the negative rail mini slammer. In all my years in electronics industry, I never have run across a mini slammer, so I'm very anxious. So mini slammer. It's sponsored by the Intel Corporation, and we're very thankful for the support. And Mr. Frank Kern is here, who is the Intel engineer responsible for the team. Again, Dr. Eric Khan is back.
Hi, good afternoon, everyone. We are going to present our capstone project, the Negative Rail Mini Slammer. Our sponsor is Intel Corporation. I'm the team member, Dora Ling. Our project manager is Mei Wu. Technical leader is Tammy Barr. Another team member is Bing Li. Our faculty advisor is Eric Sotong, and Intel mentor is Frank Kern. Before go through our project, I want to talk about the mini slammer design definition and how to use it, so you can know what is a mini slammer. The mini slammer is a dynamic load tool used to test the electrical or thermal properties of a voltage regulator. It is placed in the circuit to replicate the dynamic current significant signature of the load drawing power by voltage regulator. It is applied to by applying a control current signature. The mini slammer can identify the voltage drop corresponding to current step and overshoot associated with the current release. And the temperature release corresponds to a static load. This data can allow the power delivery engineer to modify board layout and capacitor selection to contain the drop and overshoot within a specific voltage tolerance. Also, the static testing allows the engineer to analyze or optimize voltage regulator similar response. Now let's talk about our project, the Negative Rail Mini Slammer. Why did we work on this project? The reason is the industry does not have the mini slammer design available. However, positive voltage regulators are no longer sufficient. Therefore, a new test device, Negative Rail Mini Slammer, is needed. This tool can test the necessary quantification of negative output voltage regulator by delivering transient current. It will be sold by Intel's tool group to development customers such as Intel Data Center, Intel Computing Planning, Dell, Amazon, Facebook, Microsoft, for tests of their desktop, server, mobile, and memory design. Now let's talk about our specification. Our design is capable of the following. The Negative Rail Mini Slammer must be able to supply current as following condition. DC current up to maximum of 6 amp. DIDT up to maximum of 20 amp per microsecond. Frequency between 100 Hz to 1 million Hz. Duty cycle between 10% to 100%. Also, we must be able to step the current with minimum rating while it connected to a voltage regulator with low impedance connections. Also, it must be able to support voltage between the maximum of 0 volts and minimum of negative 6.5 volts. The mini slammer must be able to support the following protection: overcurrent protection with 8.5 amp and overtemperature protection with 95 degrees. Also, it must provide accurate current measurement, and it also will be connected to wide range of capacitive load and maintain stability. The range of the capability load that this device must be able to provide is 10 microfarad to 5 microfarad. Now Tammy will talk about the basic functionality.
purpose of the mini slammer is to apply a precision transient current to the output of the voltage regulator. The frequency, duty cycle, amplitude, and slew rate of the transient current must be very precise also. In order to do that, we designed the negative rail mini slammer. Mini because it's a very small tool, slammer because it slams the current on and off really fast, and negative because it tests a negative output voltage regulator. In order to do this, there are many different functional blocks, each block consisting of very unique components. In order to design this tool, first we simulated it using multi-sim. We simulated each functional block separately and make sure that it worked according to how it was supposed to. After the simulation was working, we were able to choose and order the parts that we simulated. All of the parts here. And build materials, the BOM, then to make the schematic and start the layout. The layout was very challenging because the tool is so small, and we have power planes and high-speed signal traces, and you can't have power planes and high-speed signal traces on layers adjacent to each other, so you have to have good ground isolation between power and signal traces. After we got a working design in simulation, we prototyped all the separate functional blocks separately on these different little boards and tested each block separately to make sure that it functioned properly. After all of the blocks were working separately, we connected them together, and it actually didn't work very well in the first breadboard prototype. So after a little bit of troubleshooting, we figured out the problem, which we'll talk about later, and redesigned the prototype with shorter traces and good ground isolation, and then we were able to get a working prototype. Now we'll go into how the mini slammer actually works. So we have a function generator input that's controlled using a LabVIEW program. The function generator input comes into this first inverted op-amp, which inverts the signal and amplifies it to control this MOSFET. We're using this MOSFET as a variable resistor basically to control the amplitude of current. All the current goes through here, this resistor, which is a current sense resistor. The power across this FET can be pretty significant because the maximum voltage is 6.5 volts and the maximum current is 6 amps, so I believe that's about 39 watts. So we had to choose a DPAC FET to be able to support that kind of power. This DPAC FET will support 65 watts. And now I'll hand it over to Ben to talk about the rest of the design.
Hi. So another main component we use for our design is an inverting amplifier. We call it amplifier 2. It is used to accurately report design output current. It has a gain of -5 to be able to invert and amplify small negative current to 5 times greater positive current. It also has fast slew rate to speed up current flow, and also another important feature of this FET is that it has a power down mode, which is useful for us to design over current protection and over temperature protection for our slammer. So this is amplifier 2. It receives the voltage from the current sensor resistor, which is this one, and amplify and invert it to get a desired output current. The feature of the slammer is overcurrent protection. If if output current sent to OCP, the comparator inside OCP will compare this current with the preset reference current of 8.5 amp. Based on that comparison, OCP will send this for signal to amplifier 1, amplifier 2, and control board. If overcurrent event occurs, the yellow LED will turn on, and the negative mini slammer will shut down the load. It remains off until the user reset power. Here is the photo of the yellow LED when it's turned on, while we are trying to testing the OCP. Another feature that we added to our slammer is the over temperature protection feature. We used temperature switch as a main component for this part of the slammer. The temperature switch is placed close to the FET, which is the hot edge component when the slammer operating. It will sense the temperature near the FET and compare that temperature with the temperature threshold of 95 degrees Celsius. Based on that comparison, the OTP will send visible signal to control board, amplifier 1 and amplifier 2. If over temperature event occurs, the red LED will be turned on. Again, the slammer will shut down the load and remains off until the user reset power. Here's the red LED. It is turned on when the FET reaches the temperature of higher than 95 degrees. And May will talk about validation and results.
So we verify our mini slammer, our design using a test suite code was provided by the Intel Corporation and designed by Intel Corporation. And this is in a figure here. This is how we set up in the lab to measure the current. So we measure the current by connecting a current probe from the V out of the voltage regulator and the mini slammer. And our current measurement was 6 amp DC. For the raining, we measure the current waveform using an oscilloscope. So we measure the raining, and then we could limit the raining plus minus 10% of the current waveform. For the RAM rate, we calculate using 10% to 90% of the current waveform divided by changing time delta t, and our measurement was 20 amp per microsecond. For more validation, we test the overcurrent protection by setting the current to 8.5 on the control FET, and we were able to verify with the yellow LED lights turned on, and also we measured the current on the IO, and the actual current set dropped to 0 amp. For the over temperature protection, we measured the control FET by heating up the temperature switch, and then we could verify that with the red LED lights turned on, and also the current dropped to 0 amp as disabled signals clusters. The temperature was 81 degrees Celsius. Obstacles. We have some obstacles during our design. while we were doing the prototype, we see a lot of noise in our circuits. It was because by the crosstalk, the unwanted transfer signals between between communication wires or channels. In order to fix the problem, we made an additional plane to isolate the ground and the power and the signal traces. So we actually took longer time than we expect to design the PCB layout. In order to fix the problem, we fix it on the PCB layout. So we use additional time. Actually, we use extra time than we expect to make a 4 layers PCB in order to fix the crosstalk problem and reduce the noise. In conclusion, our negative mini slammer worked as designed. We were able to get the current and actual current it matches. And for the OCP and OPP, the lights are turned on when they sense 8.5 amp on the control fan, and also the temperature exceeds to 81 degrees Celsius. During the project, we learned to improve our prototyping, debugging skills, and design PCB, and we also learned to manage the projects. Do you have any questions?
Thank you. Can somebody elaborate on in actual use, what is the circuit doing?
It's actually used to validate a voltage regulator. It's simulating a device that would be on a motherboard, say a processor, for example. Everyone understands that. If the processor is doing a lot of calculations, for example, the current's going to be stepping up and down. This tool can simulate that current stepping up and down, and then the engineer can measure the output voltage in response to that current stepping up and down and make sure that it's stable and staying within regulation.
Let me throw a few bits of information on that. So the transient current will induce an overshoot and an undershoot on the voltage plane. That turns into, basically that's measured against voltage tolerance. In order to maintain our performance targets on the processor, we need to keep the voltage tolerance within a given range, because what happens downstream is that noise will propagate onto reference voltages for high-speed signaling. And if we get too much noise on the high-speed signaling, our communication fails. We corrupt data being passed from buffer to buffer. And so we have to maintain the voltage regulation within a given tolerance such that the loads downstream circuits do not fail. And that's the critical nature of this test. We're making sure that we stay within a given voltage tolerance such that those downstream circuits will always meet the performance targets.
So the voltage regulator you're testing might be a circuit that a motherboard designer would design for regulating voltage of a motherboard that has your processor on it?
That's correct. And the intent is to ensure that with a given volume across process temperature and voltage, we're capable of maintaining a given voltage tolerance when we have a predefined DIDT, or current step transition. And then if there's deficiency, usually what will happen is the board design will be modified with additional capacitors, or the layout of the board will be modified to basically put the design back in compliance.
And this circuit that they've designed will be essentially commercialized by Intel so that it's a specified test fixture for motherboards that would contain an Intel processor.
Either an Intel processor or some other type of Intel silicon.
Any other questions?
Okay, two questions. One is, I'm not sure where you put the temperature sensor. Is it on the case of the fan or is it on ambient air?
Is just close to the FET on the PCB board.
So it's actually ambient air?
Right, it's not like inside or
Do you expect that to rise to 95C?
Yeah, right.
Already?
Yeah, the board
That's
could.
very high.
The board goes
Right next to the FET.
The other thing is, I'm not sure what's the variability of your loading, and you're trying to control the reading to be within 10%. So if you test under all the different loading conditions, I think you have a capacity load as well. So what change impedance matching, so is that reading always within 10% of all the range you
Yeah,
interested in?
yeah. Actually, the reading didn't exceed 6%. Yeah.
Questions? Staff, back to you.